Okay, we're going to look at this problem that deals with maximizing revenue of an airline. You're going to see different variations of the numbers here, but for the most part, this is what it looks like. Okay. Um, First of all, when we talk about maximizing, we said this in class. In order to maximize something, uh, you have to have a relative maximum point. So to have a relative maximum point, you have to have a quadratic, right? You have to have a relative max. You have to have something that comes up and then goes back down. So when you're talking about maximizing, we're talking about finding this point. Now it could be a cubic that rolls back up like this, but in this case, we're looking for a quadratic. Now they want us to maximize revenue. In terms of calculating revenue, revenue is calculated by taking, the cost per item, let's say generically, and multiplying the cost per item times the number of items, right? Or the number of items sold, or however you want to look at that. But this is basically how revenue is calculated. So when you look at the information that's up here, in terms of this airline, you're looking at the cost, okay, per ticket, or cost per passenger, if you will, times the number of tickets sold. And both of these, are based on these $1 increases in the ticket price. So let's read it. On a certain route, an airline carries 9,000 passengers per month. So the number of tickets starts as a baseline of 9,000. So here's how we're going to write that. They're each paying $60. So monthly revenue, do the math here. What is that? $540,000. Okay. That's the standard is met. A market survey indicates that for each $1 increase in ticket price, so if we add $1 to this, the airline will lose 50 passengers. This will go down by 50. But this increase, it says for each $1 increase, that can happen multiple times. So what we're saying is this $1 that we're adding to the price can happen more than once. So if we multiply that times X, what we're saying here is that X is the number of increases. Okay. So we're looking at it like this. If I increase this $5, then I lose 50 passengers times 5, right? But because that independent variable can keep changing, this is what we end up with as our calculation of revenue. The ticket will cost $60 plus $1 for every increase that's made. But every time this increase is made, this affects the number of passengers. So we end up with this equation. Now, if we FOIL this out, or if we distribute this whole thing out, 60 times 9,000, I think my math is right here. That's 540. I'm doing this in my head. 60 times negative 50 is negative 3,000x, plus 1x times 9,000 is 9,000x, and 1x times negative 50x is negative 50x squared. If we clean this up, we get negative 50x squared plus 6,000x plus 540,000. Okay, this is our revenue function. Now, when we talked at the beginning of this about how if in order to find the maximum of a function, you have to have this behavior, this top of the hill behavior. This is a quadratic function, which is a parabola, and the leading coefficient is negative. So we are going to have maximum behavior like this. We just have to graph it in order to find that. Okay, so for the sake of what we're doing now, I'm just going to open up Desmos real quick. I said real quick. So we have in Desmos, if my internet works, okay, good. So the function that we're maximizing is negative 50x squared plus 6,000x plus 540,000. Now that's, you know, that's a big window. We could zoom out lots and lots of times. We're probably going to have a hard time finding it, right? I mean, even just looking at it like this. Oh, sorry. Let's go here. This got messed up. We'll say y equals negative 50 x squared plus 6,000x plus 540,000. Well, hold on. I'm not writing a point. I'm writing a function. Oh, that's what it is. Duh. Can't use a comma in here. Sorry about that. Now we could scroll all the way up here or zoom out. Okay. The y-intercept of this is 540,000. If we zoomed in right here, we'd probably be able to see this. So it's just barely visible that it's probably getting to a maximum point somewhere around, 725,000. We can change the window on here by having the y-axis go at from 0 to, let's say, 740,000. Let's see if that, and then our x values, how many increases are even possible? We could start with 0, right? But you would assume that this would be, I don't know, we could say from 100. Let's see what that looks like. What did I miss here? Okay. There it is. I keep using the comma. My bad, guys. My bad. So we see the maximum point up here at 60, 720,000. So 60 is not the price of the ticket. 60 is the number of increases. Remember, that's how we wrote our function. X is the number of increases, dollar increases specifically. Okay. And we get 720,000, which is the revenue that we're trying to maximize. So if you go back to this problem, what is the maximum monthly revenue? The revenue created by multiplying the cost per ticket times the number of tickets would be $720,000 that you get by raising the ticket prices 60 times $1. So the ticket price would be $120. So we've got that. So that if X is 60, that's the number of increases. So a ticket costs $120, but the revenue is that 720,000. Sorry about that. Don't put commas into Desmos.